Hi folks. In this lecture, we're going to focus a bit more on how to describe the state of a system. If you remember, we said that a state of a system is a description of a system in such detail that the system can be reproduced anywhere we choose. The system we will attempt to totally describe in this lecture will be the model system called an ideal gas. An ideal gas is a very straightforward system to not only completely define, but also visualize. Now, this is not a trivial system, but a wonderful first approximation that will help us in defining terms and methods that can be later applied to all pure component single-phase systems. Macroscopically, an ideal gas is any real gas at relatively low pressure. As gases become less dense, they will all start to behave like the ideal gas. Microscopically, we can generate a picture of this ideal gas. This visualization is called the Kinetic Molecular Theory. This theory is a particle picture based on several assumptions. An ideal gas is made up of very small particles where the container is much larger than the size of the particles. The particles are small hard spheres that undergo perfectly elastic collisions like billiard balls, and they exhibit no attractive or repulsive interactions with each other. The temperature is equivalent to the average kinetic motion of the spheres, and the temperature and gravity are considered constant throughout the container. So for a real gas at very low density, the space between the gas particles would be great in comparison to the particle's size. The interactions between the particles would be minimized, and the real gas would begin to behave just like this ideal kinetic molecular gas picture. Now, if we wanted to describe an ideal gas in enough detail that it could be set up perfectly in another lab in an exotic location, how many and which physical properties or state variables would need to be quantified to make this possible? Well, for a single component gas, 4 physical properties are all it takes to describe the system. If we know the moles of the gas N, the absolute temperature T, the pressure P, and the volume V, we know everything about the ideal gas that there is to be known. These 4 state variables establish the exact state of the system. Now it's off to France to set up the gas. But wait, it turns out that a rule derived from the fundamental laws of thermodynamics called the phase rule proves that we only need 3 of these variables. Why only 3? Well, this is where the kinetic molecular theory comes in. Utilizing some Newtonian physics and some statistics, we can take this picture of our gas and derive the following equation. PV equals nRT, which is called the ideal gas equation of state. Notice we know something about all the state variables or measurements in this equation, PV, N, and T, except the value R. This is a universal constant of nature that begins showing up in not only this context of ideal gases, but in many other places in the scientific world. Really amazing. So looking at the equation again, if R is a known constant of nature like pi or the speed of light, and I know any of the 3 state variables for this ideal gas, the 4th property can be calculated and is fixed using this beautiful equation. The phase rule is correct. For an ideal gas, I only need 3 state variables, and by using the ideal gas equation, the 4th can be calculated. Now, let's get at the value of R. Let's first rearrange the equation to be R equals PV divided by NT. We will assume SI units for pressure, which we know is pascals, and SI units for the volume, which we know is meters cubed. We already know that N will be the number of moles for the gas, and finally, we know that the temperature T will be in the units of the absolute temperature scale, Kelvin. Plugging these units into the equation, the SI units for the constant R will be Pascal meter cubed per mole Kelvin. In SI units, R equals 8.3144621 Pascal meter cubed per mole Kelvin. This is not an exact value, but a carefully measured value that has even more decimal places than what I've written down here. Now, we find that for the derived unit for the energy in one of our earlier lectures, that pressure times volume, which we see in the numerator of the R constant, Pascal meter cubed, is equivalent to the units of energy in joules. So we also can say that R equals 8.3144621 joules per mole Kelvin. Cool. We know many conversions at this point, so it should be rather straightforward to calculate R in other volume and pressure units. I've shown on the slide how we can compute R in the units of centimeters cubed torr per mole Kelvin. We want to use the equation of state to solve some typical ideal gas problems. In doing these problems, we first want to figure out which R value we want to use, then convert all our given values to the same units that is in our R value. We then rearrange the equation to solve for the variable we desire, and finally, we're sure to answer the problem in the units that were asked, which might mean a final conversion at the end. If we have 1 mole of an ideal gas at a temperature of 32 degrees Fahrenheit and a pressure of 1 bar, we should be able to obtain the volume of the gas in liters utilizing the ideal gas equation of state. The way this shows up in a solution map is that we take N, T, and P, and we find V utilizing the ideal gas equation of state. Now, I tend to only remember one value for R, and that is the SI version, which is R equals 8.314 joules per mole Kelvin, which is equivalent to 8.314 Pascal meter cubed per mole Kelvin. So my solution map is modified just a bit, since many of the given values in the problem statement are not in the same units as my R value, so will not cancel out correctly when I use my preferred value for R in the equation of state. I figure that the given values have only 3 sig figs, so 4 sig figs in the R constant should suffice. Now, if I want to use this particular value of R, 8.314 Pascal meter cubed per mole Kelvin, I need to make sure that all my other given values are in the same units for the temperature and pressure. I will need to convert my given pressure in bar to the equivalent pressure in Pascal and my temperature from degrees Fahrenheit to Kelvin. Now, it's very important to remember that the temperature always must be in an absolute temperature scale such as Kelvin. So if you find yourself with a temperature in some unit other than Kelvin, just automatically convert it. Also, we need to remind ourselves not to round off any of our computations, but to keep track of the sig figs with underlines. So after the temperature conversion, we have 273.15 Kelvin with 3 sig figs because the original temperature had 3 sig figs, and for the pressure, we have 1 times 10 to the 5th pascals marked at 3 sig figs because the given pressure in the problem statement had just 3 sig figs. Now we want volume. So we solve the equation of state for volume algebraically, obtaining V equals nRT divided by P, and we finally enter all our known values into the right side of the equation. We know everything is good if all the units cancel, leaving us with only the volume in meters cubed since all the state variables and constants are in SI units. So we get a computed volume of 0.022710 meters cubed. The problem statement wanted the volume in liters, so we multiply by 1,000 in the last step of the map using the relation that 1,000 liters equals 1 meter cubed. And finally, we round off to 3 sig figs, obtaining the answer 22.7 liters. This example we just completed is also a special case. When temperature is 0 degrees Celsius or 32 degrees Fahrenheit, and pressure is 1 bar, we call this STP, or Standard Temperature and Pressure Conditions. The standard was established by the International Union of Pure and Applied Chemistry, or IUPAC for short. We see from the computation that at STP conditions, 1 mole of an ideal gas takes up 22.7 liters of volume. Now, that being said, you're going to find many textbooks defining STP conditions at pressure equals 1 atmosphere and temperature 0 degrees Celsius. If we do the same computation as we did before using these slightly different conditions, we will find that 1 mole of a gas would have a volume of 22.4 liters. Go ahead and check this out for yourself, okay? So what does this mean? We have to be careful to check what standard convention is being utilized when working on ideal gas problems. So bottom line, for the state of the system of matter called an ideal gas, if we want to recreate the gas system somewhere else, we only need to know 3 of the 4 variables, N, P, T, or V. The 4th variable will be fixed and can be calculated utilizing the ideal gas equation of state, PV equals nRT. So, the phase rule was correct. This lecture was an amalgam of the macroscopic and microscopic views of matter. It also demonstrated the complete understanding of a system, something we strive to achieve all the time in chemistry. Macroscopically, we characterized our bulk matter, the ideal gas, using several properties of matter, such as temperature and pressure, volume, mass, and moles. And we're even able to establish the state of a system completely. More complicated systems can be characterized similarly, though we'll need to define and quantify more state variables and properties to do that. Microscopically, we gained considerable insight into what an ideal gas might look like via the kinetic molecular theory. In later lectures, we'll describe even more complicated systems at the fundamental level of atoms, slowly building up to more complex matter as we look at the nature of the chemical bond. Both views, macroscopic and microscopic, are critical in understanding chemical reactions and physical changes, and we'll strive to clarify and enhance both ways of knowing as we move forward. Should be a lot of fun. See you next time.